All right. Good morning, everyone. Thanks for coming. Nice to see everyone here in person. I'm going to say a few words that Emma passed to me and that Richard has not yet vetted. I think all of us, are super happy to see the esteemed Richard McDermid back in Hawaii. So Richard is now director of the Australian Astronomical Optics at Macquarie University in Sydney. Doing very well. Richard works on studying stellar populations and dynamics of galaxies, understanding galaxy evolution. He's also working heavily in instrument development, including GHOST here at Gemini. And he's now project scientist of MAVIS, which he's going to tell us about today. Richard got his PhD in Durham in 2002, had a postdoc in Leiden, and then I couldn't believe it, but he actually came to Gemini as a science fellow.
Yeah.
And then he moved to Australia in 2013. I could not believe that number either. So yeah, I overlap with Richard, and it was great to have him here. He helped out with NIFs quite a lot.
Quite a lot.
I think we will still find that some of the IDL codes that we run here
Yes.
The ones that don't work anymore.
are still being used. Anyway, it's great to have you here.
Oh, thank you, Andy, and it's great. It is great to be here. And it was great catching up this morning with everybody. And can't quite believe it's been so long since I was here last. I think it was, before the little pandemic that we had, and there's been a few changes around here in that time on top of that as well, getting up to speed on that. But it's always such a pleasure to come back. I'm actually here on holiday, which is of course why I'm here giving a talk. But I'm over here with my family and catching up on some old family memories, all the fun places like the mall, Walmart, things like that.
We turned on the volcano for you.
Thank you for that. Yeah, we just happened to be there at the right time, and that's was a highlight. In the 6 years I was here, I never saw actual 600-foot spraying lava coming out of Halemaumau, so that was a real highlight. So it's been a fantastic trip, and it's a real pleasure to get the chance to come catch up with everyone, and this gives me an excuse to do it. So yeah. Good, but I will warn you that my brain is in holiday mode. So when I was planning the trip, it seemed like a really good idea. But now 2 weeks into the trip, I'm like, what? Science? What? So forgive me if I go astray. But I thought I would give you a little overview of a project that takes up a fair bit of my time at the moment, and has done for a number of years, which is this facility instrument for ESO's UT4, or the Adaptive Optics Facility Telescope, the one that's kitted out with all the lasers. And I thought this was also maybe timely given the AO upgrade that AO's involved in here at Gemini. They just had the PDR at the end of last year, and I know there's sort of exciting potential overlaps around adaptive optics and what that capability might look like. And I think MAVIS is kind of the evolution of what I think is kind of the cutting edge of this kind of general purpose adaptive optics from a facility point of view. And I'm sure you're going to have kind of really good, difficult questions for me that I haven't thought about, but that's good. So it builds on the shoulders of giants. The real investment, I think, for MAVIS that's capitalizing on is the adaptive optics facility itself. This is a major project from ESO from more than a decade ago, equipping it with multiple lasers. The deformable secondary mirror, of course, is the key part. And it's been incrementally, I guess, probing what it can do. And maybe this is kind of like the current status of that. Okay, but I'll get into more details about what it is. So why am I here as an Australian citizen now, talking about European Sun Observatory Facility Instrument? Europe is pretty far from Australia. I think it's hard to get further from Australia. So what gives? Well, it turns out that Australia actually kind of joined ESO as what they call strategic partners. So this was a 10-year sort of fixed term deal that gave Australians access to Paranal and Lucia facilities. So There's no ELT promises. There's no Alma access that comes with it, but for Lycia Parnell, everything was available, all the telescopes, but also going for contracts, including instrument contracts. So that was a great opportunity for Australia to sort of put a foot in the water with ESO and see if that was going to work for us. And having that opportunity to go for instrument contracts was, of course, a major part of the return on investment story that Australia wanted to build. At the same time, you know, the AOF had been commissioned. This was getting put through its paces. The MUSE GLAO mode was fully operational at that point, well tested, delivering great results. They were moving towards getting the narrow field mode, which is when they bring the lasers in and they do the tomography in the central sort of 6-7 arc-second field of MUSE. That was just getting commissioned at that time, but it was going well. So this was working very well. And they're like, well, MUSE seems to do pretty well, and it wasn't really designed for giving you kind of close to diffraction limited performance of this telescope. MUSE was really all about the wide field, and this high resolution mode was kind of an add-on. I was involved in MUSE as well in its early stages, and we really had to argue for that narrow field mode capability. But actually, the telescope was delivering it very well, with just one deformable mirror being the secondary at that time. And so there was a kind of a combination of opportune timings that became an idea in the community that maybe they could do more of a facility multi-conjugate AO system, delivering close to diffraction limit at optical wavelengths. And that's the kind of novel part, is trying to do adaptive optics in the visible. And that remains the key challenge, but MUSE works in the visible, it's delivering good results. So we have lots of reasons to think that's a good thing. So all of this kind of came together. Australia went for it. We put in a bid, and we won the phase A to do the study for the instrument that became MAVIS. So why would you want to do that? Well, this is how MAVIS in the orange here kind of fits into the landscape of facilities that are coming online. I've been giving this talk for a while, which is why it starts in 2020. We're now like already over here. And these arrows kind of shift to the right every year, by a year, some of them. But the idea is that the future facilities that are going to be operating in the 2030s, they have some commonality, right? They're pushing on sensitivity and they're pushing on angular resolution. And so, you know, the infrared, even down to the radio wavelengths, we're going to be opening up new regimes of spatial resolutions and sensitivities that we haven't been able to do before. And part of the missing piece is delivering that same combination at optical wavelengths. And that's why we see MAVIS as filling a niche in trying to deliver that kind of high resolution, high sensitivity on a large telescope, but at optical wavelengths. And just to put this kind of onto a graph, this is a picture of showing sensitivity on the left with wavelength and angular resolution in arcseconds on the right against wavelength. And some curves here, some of them known, some of them hypothesized. And where would MAVIS fit into this? Well, it's going to be in the sensitivity regime that we'll get in the infrared from ELT, currently from GWST, but with the angular resolution of ELT-like capabilities. And it's that combination that makes that opportunity to put diffraction limited optical capability on the 8-meter telescope kind of makes sense. Fills a bit of a gap there. And then from a science perspective, the optical, of course, is a very information-rich regime. It's a well understood regime. Many of our calibrations and calibrators are available in the optical. So if we launch into an infrared regime in a new angular resolution regime or new sensitivity regime without that knowledge from the optical, that may pose some issues that we would really want to have that optical capability. You can get very sensitive in the optical because of the low background, great detectors, large formats. A number of things are easier in the optical. I don't have to tell anyone in this audience, a little easier in the optical than they are in the infrared. And that brings with it sort of enhanced capabilities. And then this key one here is that, you know, if you're getting the diffraction limit in the optical, that's a great complement on an 8-meter telescope, is a great complement to the diffraction limit at 2 microns on the ELT or an ELT scale instrument. And just to give you that kind of synergy, you know, we were looking before at a GEMS and an HST picture. If we go visible 8-meter diffraction limit from the ground, we'll be able to complement what we're getting on the ground from something like MCAO ELT or equivalents on GMT, TMT. So that synergy with the next generation of large facilities is also key for MAVIS. Okay, and then just to give you sort of a sense, you've probably seen this already. This was like an early press release about how the Muse narrow field mode is doing. So this is your wide field mode, just in CN limited, and then you switch on your laser tomographic AO and out pop all the stars. This was an early one. And this one I like because it's a direct comparison against something we're quite familiar with, which is HST ACS. And then what we're getting in Muse narrow field mode at comparable bands, spectral bands. It's very wavelength dependent. But you can see that you are into that regime, both from a sampling, but the actual quality of the PSF is excellent. So Muse narrow field mode is very powerful, but it has some strong limitations. You have a fairly limited field of view. So your patrol field, I think, is around 6 or 7 arc seconds on the infrared wavefront sensor. It's single conjugate. And so it has a very small sky coverage. There's a very small number of places where you can actually deploy this great capability. And that's one of the key limitations that we want to get over with MAVIS, in addition to having an imaging capability and some higher spectral resolution, some other things I'll talk about. But based on this, there's a strong motivation to take on a more capable instrument. So a little bit about the consortium. As I said, Australia is leading this. So between AO and ANU, we have an entity in Australia that we call Australis. And this is basically a national collaboration between 3 institutions: AO at Macquarie, the AITC at ANU, the Advanced Instrumentation Technology Centre, and then the University of Sydney. So by having this kind of collaboration approach, we get to make use of the capabilities of these different groups, but through a single funding channel. And that allows us to go for big things like an instrument like MAVIS. So Australia is about 50% of the project. The other 50% is based in Europe, mostly with the ENAF community in Italy, with a few partners, the main ones being Arcetri and Padova, those being the real kind of powerhouses for adaptive optics in Italy. We have Laboratoire Marseille, the LAM group, who I think are also involved in the GNAO project. And then finally, ESO itself is kind of a partner. So they're doing some things around the detector systems and the infrared wavefront sensors. They're kind of part of the consortium, but also the customer, if you like, which has its own peculiarities. So unfortunately, this map is not to scale, and these places turn out to be fairly far apart. And so that itself, both geographical but also time zone difference, makes this a very interesting project to work on. My evenings used to be full of dinner and Netflix. Now they're full of telecons with Europeans. But that's fine. That's what we do. But the real interesting thing is it's a very complicated instrument in terms of it's an integrated AO bench and science instrument capability. It all sits on the Naismith platform. It's a very integrated system. And that's because when you're trying to do this kind of challenging AO in the optical, all of your error budgets just like shrink to nothing. We have a wavefront error RMS tolerance of like 120 nanometers or something like that. That's end to end. So everything is very, finely balanced. And you're trying to do this in a consortium that really spans, the globe. Is one of the ongoing challenges. It also means that we have 2 summer holidays in a year, things like that. So it's been an interesting experience to see how does Australia collaborate with Europe on this kind of complex things. So that's the consortium. That's a picture of us when we got together in Asiago. Some of you will know this gentleman here. That's the principal investigator, Francois Rigaud, who is part of Gemini North and South, I think, and was involved with Altair and, of course, with the GEMS MCAO system. So Francois is kind of the brains behind the complexity and innovation, I think, of the adaptive optics system around the real-time control system. And it's great to have his experience on board and various others here from across the consortium. And I think this was the last time we were all together because then we had the pandemic, everything went remote. So interesting. So that's the group. A little bit of an introduction to the instrument. If you are interested, there is a Messenger article, which is a nice kind of top level overview of the instrument and some of the science. So feel free to check that out. Came out a little while ago, but here we have it kind of on a page. So it's multi-conjugate adaptive optics. By visible, we mean from 370 to 935. So it's really the near UV to the near infrared. So it's a very broad spectral range. That's the science channel, and all the infrared light is then used for the natural guide star wavefront sensor. And then, of course, we have the lasers at 589. The top level science capabilities of the instrument are in the imager. We have a 30 by 30 arc second field of view on the imager. Huge, right? But it's a lot of resolution elements because our PSF should be down around 15 milliarc seconds. So a 30 arc second field of view is actually quite big in terms of number of resolution elements. So that's the imaging capability. Then we have an IFU. We did a kind of a trade-off against a number of different spectral capabilities, from multi-object to slits, to micrometers, to moving IFUs, fiber bundles. And the most sort of generally usable technique for doing the spectral capability turned out from that study to be a contiguous field IFU. So this will be an image slicer based, like NIFS was or Geners now, image slicer based, and we were then limited by the amount of detector real estate and optics that we could afford, basically. So we came out there with a 3 by 3 arc second field like NIFS, but with 25 milliarc second spatial sampling. And that's great, but that's when you're delivering kind of your better performances. But we also know that we're going to do extended sources. We won't always have the best conditions. And so we have an image scale optic that changes your 25 milliarc second spaxels to 50 milliarc second spaxels, and of course then doubles the field of view. So that's the approximate IFU field of view. And then that's feeding 4 spectral modes, which I'll talk about in a little while. The goals here from Strel ratio, while this is how you define a diffraction limit is an endless discussion, especially with adaptive optics people, but this is basically a lowish Strel system, and that's because they were working in the optical. So, you know, Strels of tens of percent just aren't very realistic unless you're going to, you know, all out on an XAO on axis kind of system. This is more about delivering a high level of correction of a large field of view to enable the science that comes with that. So Strel is about 10%, maybe 15 at the goal for the median conditions that we assume. And then the other thing that we really want to push on is the sky coverage. So we really want to open up the sky for adaptive optics and not have it be, you know, first you have to think about your guide stars and then you think about your targets. You want to flip this so you can really think science first, and then you have a pretty good chance of being able to get your target with MAVIS. So it's 50% sky coverage at the galactic pole, okay? So away from the Milky Way. Dearth of stars, but typically that's where all the astronomers want to look. So if we can get 50%, I think we'll actually exceed that for some of the guide modes that we offer. Okay, so what can you do with that? Well, that gets you down to sort of V-band magnitude, limiting magnitude on a point source of around 29 in about an hour. So it's very high sensitivity. And I'll go through some other of the performance metrics later in the talk. And then from the tech side, we've got 4 laser guide stars that we actually split each of them into 2 beacons. So we have a ring of 8 sources around the field of view. Then we have the 3 natural guide star wavefront sensors operating in the infrared. And then we have 3 deformable emitters. We've got the deformable secondary emitter on the telescope. And then we have 2 internal DMs on the bench. And all 3 are working together, you know, fed by the real-time control system and delivering as uniform and as sharp an image quality across the field of view as possible. So that's it in a nutshell. And then we did develop a fairly substantial science case. So if you're really interested, you could check that out. It's on AstroPH as well, but I'll give you kind of a snapshot of it over this talk. Okay, so that's what the CAD model looks like. So it's an interesting design. The beam is coming here from the telescope, from the bottom right, into the optical bench. The calibration unit is going to sit here next to this person, kind of inside the instrument. We're not sure how this person gets out. Maybe there'll be a rope or something for them to hold. So there's space around the gantry here. Calibration unit here, and then this kind of cylindrical piece that's underneath the bench. That's a rotating carousel that does the laser guide star wavefront sensing. So remember, there's 8 wavefront sensors configured here. and they will rotate as the telescope tracks because the rest of the bench is static, right? So they will move with they will move with the pupil, and they have to rotate and track. So that's an interesting design feature on this turret. And then the optical beam, there's a dichroic here for the sodium light. Then the rest of the beam comes through here. There's a dichroic that cuts off for the natural guide star wavefront sensor, the imagers on the straight through path, and then the spectrograph has a pick off to send it to the IFU. So that's the CAD model version. Here's kind of the optical path. So again, telescope on the left, coming through a field lens that brings the beam immediately onto the two deformable mirrors. And then we have our dichroic here for the laser light that gets sent down into that turret that's rotating over the sky on the sodium light. There's a ADC, so to correct for the refraction of the atmosphere. There's a K-mirror to stabilize the field, and then pass that through to the natural guide star wavefront sensors, then the science channel to the imager or the IFU. So it's quite a complex instrument, but it has to be. That's the nature of it. Another way of looking at this is kind of a snapshot. So as I said, they have the 8 laser sources. Then we have our science field of view. The technical control field for the natural guide stars is a 2 arc-minute diameter field. So it's a fairly large technical field to pick off your 3 NGS stars, up to 3. And the natural guide star wavefront sensors will be equipped with multiple wavefront sensor, like there's a singlet, and there's a 2x2. And there's a higher order one for calibration purposes. So each of the arms has multiple guide modes within it. So we can do different combinations depending on the brightnesses of the stars, different guide rates. We're talking about things like the old open loop mode for the laser, where we may have limited tip tilt brightness, natural guide star brightness for doing tip tilt focus. So it's very, very flexible, quite complicated arrangement. Back to the IFU and spectral mode. This is wavelength now against spectral resolution. I mentioned there are 4 spectral gratings in the instrument across the 2 arms. So the IFU has 2 arms. The field is split in half, 2 arms, and then each arm is equipped with 4 gratings. I think the workhorses are going to be these low resolution modes, which are actually still about double the resolution of MUSE, spectral resolution of MUSE, around R5000. And then we have a high resolution red and a high resolution blue mode. And these were geared from consideration of that science case I mentioned. We wanted, ideally we'd have a full suite of all resolutions and so on, but there was a limited budget for that. So we really went to the science case. We picked up what was really needed. And so the LR blue, this is really driven by looking for, things like hot young stars, ionized gas. The O2 doublet, for example, pins our 370 nanometer requirement at the blue end, things like that. So that will be important for ionized gas, things involving star formation and so on. The HR blue, this was driven by the ability for MAVIS to dig into the densest stellar systems, like the centers of globular clusters, and actually start to pull those apart, beyond the crowding limit of HST. And the kinds of things you want to do there are, good radial velocity accuracy for doing things like maybe intermediate mass black hole. And I'll talk about that from the imager point of view as well. And also doing things like detailed abundances. So actually elemental abundances in these unexplored central regions of globular clusters. The HR red was really driven by pushing out to higher redshift systems, but also doing more detailed consideration of the line profiles in galaxies. So looking at line shapes, not just measuring their widths and their velocities, but actually looking for multiple components in emission line systems. You need that higher resolution to do that. And then the low resolution red was to get all the red shifted versions of the things you might do in the local universe, and particularly pushing out Lyman alpha to do follow-up of things you might detect, for example, with MUSE in the wide field mode. And then you can go do follow-ups and look at its spatial structure with MAVIS. Okay, so those are the spectral modes, and then this is how it complements Blue MUSE, which is a new instrument that's coming for one of the other UTs. So Blue MUSE is kind of a blue optimized version of MUSE, non-adaptive optics, no ground layer, so really driven for seeing limited blue exploration, and it's around this R4 5000 as well, but seeing limited. So MAVIS ends up being quite complementary to both MUSE and Blue MUSE in that regard. Any questions?
Are the LR and the HR tied to the plate scale that you mentioned before?
No, it's decoupled. So yeah, there's two spatial modes for each of these. Yeah, exactly. Okay, so a bit about the science. So as I said, the science case is online on the archive. It kind of breaks into these sort of four broad topics. But the idea here is that we're really covering a full gamut of science capabilities, from local things, even in the solar system, all the way out to the highest redshift things that we can see, globular clusters and resolving stars. So I think this was initially this instrument was really envisioned as an imager only, but this really felt like to us and to the community that it would be really great to have a spectral capability, given all of the effort going to correcting the beam. It's a shame to not use it for spectroscopy as well. And that really enriched the science case as well. And yeah, having all of this case, I think really helped us sell the instrument to have that broader spectral capability as well. Okay, so one of the things that MAVIS hopes to do, and it was kind of a new topic for me when I got involved with this instrument, was doing astrometry, precision astrometry. And so one of the main drivers for that is to detect intermediate mass black holes. Globular clusters are a key hunting ground for these things. There's been a lot of papers going in each direction, I think, over the years as to whether they're there or they're not there. I remember even Gemini GMOS papers doing, velocity dispersion measurements with GMOS, trying to figure this out. So this is an ongoing topic. There's a nice paper recently, actually, that found some high velocity stars in the center of the globular cluster, which I think is also quite exciting, something we could tackle with MAVIS. But having the high angular resolution, you can start to look at how things are moving over relatively short time baselines, and especially if you have historic data from, for example, HST. However, astrometry is rather challenging for this kind of instrument because there's a lot going on in your beam, in the correction process. Things like plate scale, non-uniformity in that plate scale. There's a lot of opportunities, let's say, for astrometry to get compromised in an instrument like this in the process of sharpening up the images. So this is one of our most challenging science cases, I think, is to try to meet our requirement here, which is an accuracy of 150 micro arc seconds. So the PSF is like 15 milliarc seconds. You want to get 150 micro arc seconds in terms of knowing the distance between point sources of 1 arc second separation, I think is how it's technically set. Now, with 150 micro arc second astrometric precision over the course of 5 or 10 years, that gives you a kind of an effective velocity dispersion sensitivity, which is what you need to see the stars moving around a massive object like an intermediate mass black hole, of around several kilometers per second. So that's really the regime you have to get into if you want to distinguish with or without a black hole in your dynamical modeling of these systems. It's challenging for HST because it hits a crowding limit in the inner regions. So it can be a crowding in terms of source confusion. You're also running out of sources because you're down in just that central patch. So you're only seeing maybe 1 or 2 brightest objects, which you actually need to build up a sense of the spread of motion in that region. So there's lots of reasons why HST actually finds it quite hard to get into the kind of central regions where you expect the signature to be strongest. And that's the benefit of MAVIS being able to go above the resolution of HST to actually probe that inner crowding limit that HST has. So this was a nice study done by a PhD student, then PhD student at ANU, Stephanie Monti, looking at, so we were concerned about all kinds of things for this science, but the primary one was the spatially changing PSF. Right? So multi-conjugate AO, it's fairly uniform, but it's not completely uniform. You still have off-axis effects depending on the guide stars and some details of the observation. And this is kind of new, like how does that influence your astrometry? So this was a really nice work by Stephanie, who used a combination of PSF models, and you can see in the blow up here that in the central regions you have this nice correction. When you go outside of the control radius, basically of the field, so this patch here is outside of a required area of correction, you start to get some elongation effects and some sort of funny looking PSFs. So it shows you, it gives you an idea of how tricksy it is to get the PSF uniformity across the full science field. But the main point of this study was to see how will that affect our astrometry measurements, having that variation in the field. And the net result was that the black points here were measured with MAVIS, and then the red and the green are variations of the model with and without the black hole. So basically, if you can detect the uptick here in the green, then you would make a positive detection of the intermediate mass black hole, and indeed we could recover that from the simulated observations. So that was the main effect in this simulation, was around instrument things like sensitivity and pixel scale and so on, but the main thing was the spatial variation in the PSF. We're now starting to introduce other effects here, like having a multiband PSF. So this is a monochromatic PSF. Then within your filter, you have a spread. So that will also soften the PSF a bit. There's interesting things around the ADC, which is actually quite challenging. If you have to correct, atmospheric refraction at 400 nanometers, when your pixel scale is 7 milliarc seconds, no one can actually tell you what the atmosphere does at that level, right? There are no real measurements of atmospheric refraction at those wavelengths at those spatial scales. So you're very dependent on which assumptions you've made about your model, Philip or whatever. All those little details start to become quite a big, it's not trivial. That's the thing that scares me the most, actually, is what we're going to see. So we're adding kind of levels of reality to the simulation to see how well this stands up as we know more about the instrument and its design. Then this is around the spectral resolution mode. So as I said, we tuned the high resolution blue mode to kind of capture as much information within the pixel budget that we had at the resolution that would still allow us to do the science. So this is trying to do, very crowded field spectroscopy, but not just doing like age and metallicity, but digging into individual elemental abundances. So you can actually understand, what's the origin of those elements, because that gives you that insight into the formation scenarios for those stars and for those objects. And so we ended up kind of targeting this region here, which is a nice peppering of these different nucleosynthetic pathways. And just to give you sort of a comparison about how the high resolution blue of MAVIS will compare to something like MUSE, which is also doing really interesting work at the moment with crowded field spectroscopy, doing 3D extractions, so on. But that is your MUSE spectrum. It's just that broad wiggly line. So provided you can get the silver noise, of course, then you have a much richer spectrum at that higher spectral resolution. And this is point sources. That's where, in principle, the AO benefits you the most. Something a bit closer to my field of study is resolving galaxies. And just to give you an idea of what does a galaxy look like when you see it with 7 milliarc second pixels, well, we can simulate that by using a nice nearby galaxy like the Large Magellanic Cloud. I'm just going to zoom in on this one little interesting complex here on the Large Magellanic Cloud, and then we're going to put this at a distance of around 50 megaparsecs. All right, so we just take that. This is from some nice local survey, and then we just pretend it's at 50 megaparsecs. What does it look like in different spatial regimes? So here we have our 0.4 arc seconds per pixels. This would be like the no adaptive optics version. You can kind of see, how it relates. But if you zoom in on an individual complex, it's kind of, you can see it's different, but not much more than that. Then you could put on your ground layer AO, which is what MUSE Widefield model is using at the moment. And you start to see it's maybe not just one blob, but there's something else going on. And as we go down in angular resolution, so we're coming into like what HST would show you. And then finally, what you'll see with your 7 milliarc seconds per pixel for resolution. Now, this is a simulation. This is a pixelation of an image, okay? But it does make quite a striking impression about how galaxies will start to look on a regular basis when we're working in this regime, whether it's MAVIS or ELT. There's a lot of complexity here that we never really had to worry about too much, right? There's a Gaussian law, okay? And then it all starts to look a bit complicated. And it's scary for observers. It's much more scary for the theorists who have to deal with this. Being able to push out in distance, of course, gives us access to not just our nearest dwarf galaxy, but into completely different environments with unshared histories into the Virgo cluster and beyond. And this is what we should get used to doing, right? Is thinking about galaxies at this level of complexity, and how do we cope with that? How do we learn anything from this other than it's complicated? How do we push past that? I don't know the answer to that question, but we're going to have to figure it out. Another thing we can do with this high point source sensitivity, we can start to look at resolved stellar populations at also much larger distances. So we can look well beyond the Milky Way and still see an individual star or two or many. So this is a, a simulation here with CEN-A, which is only like 3 or 4 megaparsecs away, but it gives you the impression. So this is at a radial distance, which is actually becoming quite low surface brightness for doing things like integrated light spectroscopy. So if you just go there with a slit and try to get a spectrum of that region and try to do some kind of integrated light analysis, it's actually becoming quite difficult. But that's exactly the kind of regime where you start to get low enough surface brightness, i.e. stellar density in your field, we can start to pick out individual stars. So this is quite complementary to what you might do with integrated light spectroscopy in the bright, high surface brightness regions. In the lower surface brightness regions, you can start to do this kind of resolved stellar population color magnitude diagram analysis. And the benefit there is not just the radial coverage that you can get, but you actually have a much more precise tool for old ages in particular. Right, so between 10 and 14 gig years from an integrated light study, the spectra look basically identical. Right? You need signal to noise of many hundreds to really see any tangible difference between this kind of age difference in integrated light. But from a photometric point of view, it's the difference between the red and the green lines, which is, you know, several tenths of a magnitude. So provided you can calibrate all of these things, which is, you know, again, this is very idealized. But this is the color magnitude diagram extracted from this stellar field at the surface brightness of CEN-A at 4 megaparsecs. And you have clear structure here to tag on to key into with your models. And you would clearly differentiate in this case, this kind of old age difference. So that's just one example. But I think this kind of resolved stellar population study is going to be very important. The other reason is because of its, again, complementarity to the infrared. So the top line here is simulations of the same stellar field, but making different assumptions about the PSF from, on the left, HST, JWST, ELT, MAVIS, and then the K-band version of that. All of the other 4 are in the I-band, effectively I-band. So that's to be fair in the comparison. At these red wavelengths, you know, HST is struggling because it's a small telescope. JWST is struggling because the system is not optimized for those kinds of relatively short wavelengths for JWST. It just doesn't have the intrinsic image quality. And ELT, a bit the same. It's not really optimized to work, you know, much below a micron. It will deliver there, but it struggles. The MAVIS I-band is probably the best of them all and is much more comparable to what the ELT will do in the K-band, where, you know, it is optimized for this, and the AO correction is really working. So this is where you have your better synergy. And I can see I'm going to get a question here from my slide. I don't believe this guy.
I'm confused why the K-band of Mikado looks so bad.
Well, this may be an
That's
old.
where the ELT is optimized, no? That's
Yeah.
the best you can have.
Yeah, but that's
It's the-
maybe not the latest PSF. This was from the Padua. I called it like advanced ETC tool where you can make this kind of simulations from a few years ago. So it may have changed a little bit, but
Because the diffraction limit of the 40 meter telescope should be slightly better.
slightly better. Yeah. I will ask the questions. We're actually having a science meeting with them in a couple of months to explore these kind of synergies. So that would be a good place to revisit this, make sure we're doing the right comparison. Yeah. In any case, I think this sort of optical to infrared combination of the two facilities is going to be where the real value is. For this particular science case of old stellar population analysis, this is a little confusing, this graph, but basically the vertical changes in these lines represent the difference in magnitude for a difference of age compared to a 14 gig year population. So it's like 14 gig years minus 12, minus 10, minus 8. So it's kind of your age sensitivity. The higher this line, the more sensitive you are to the age difference between old populations. And then the blue band at the bottom is kind of your image accuracy, your photometric error. So it's like a 5 and 10 sigma. So if you stick above this, you have a measured difference in color that allows you to interpret it as a difference in age. So MAVIS alone, the bright end is here. This is probably all we'll get at large distances. This is like your TPRGB phase. This is your main diagnostic region for the bright tip stars. So MAVIS on its own does okay. MCAO only, which is J minus K, is not very sensitive to age differences in all populations because you're just, you know, in the Rayleigh gene's tail. So you have a temperature difference of two cool things. So it doesn't really show much. But when you use the two together, because of that long wavelength baseline it gives you, you really kind of maximize your sensitivity to, in this case, age. It's just another way of showing that synergy, provided you can see the same stars, you can really do interesting things on the stellar population side. And again, the points for sensitivity, this is JWST, a relatively recent paper from a couple of years ago now, that was looking at color magnitude analysis with JWST, which is also a big step forward from compared with HST, which is this one on the right, in comparable observation times. And that sort of V of 29 performance in 1 hour of MAVIS means that you can be matching your JWST performance within a few hours. And this sort of 29, going much fainter than 29 with HST is a real struggle if it's even still in the sky in the 2030s. Okay, one of the other key science cases that came out was resolving complex line profiles in galaxies. This was kind of driven from a top-level perspective of the apparent connection between disk settling or the change in the velocity dispersion of galaxy disks over cosmic time. So people looking at ionized gas and also molecular gas at relatively high redshifts, we're seeing that disks there seem to be hot. They seem to have high turbulence. And this could be a regulator of star formation, which is, of course, important to how that disk will evolve and form stars over time. And there's pretty good coverage at high redshift. At low redshift, we have a couple of local objects, but there's a bit of a gap here at the intermediate redshift ranges. And the prediction would be that the dispersions or the widths of the emission lines you have to measure are kind of too narrow to reliably do with existing facilities like MUSE. And so this was one of the motivations to have this RF 10,000 mode for MAVIS, was to really dig into this kind of relatively dynamically cool gas and explore for things like what is causing changes in the dispersion of the gas. Is it just the radial motion, like a real dynamical turbulence? Is it winds and outflows coming from star formation in the disk that can broaden the line, but it's nothing to do with its dynamical state, it's to do with its star formation rate. So that was one of the motivations there. And just to sort of illustrate the benefit of going to high spectral resolution, at the top we have the same complex, but at the top here with MUSE, where you have this R of a couple thousand. Someone has to go. I remember that. Whereas if you see the high spectral resolution, you start to see this is actually a double line component, right? So you have probably a gravitational and a non-gravitational element to this inflow, outflow, this kind of thing. So these things become quite hard to detect unless you have high spectral resolution. And this is built from a simulation here on the left. And then just going into deep imaging in the optical to understand what the optical or rest-frame UV morphologies of high redshift galaxies actually are. So here we have another simulation where we're comparing a model here on the far left with the different instruments that we mentioned before, HST, ELT, JWST, and then MAVIS at the far end. And just to show how both the PSF and pixel sampling of MAVIS really help you. It's the one that looks most like the model, basically. It's the bottom line of that plot. And the other simulation on the bottom right is comparing like a deep field. So I think this is 10-hour integration with HST, where you just have the smaller telescope and making full use of the 8-meter telescope with MAVIS, and that you start to see not just blobs, but you see if it's a disk or something like a spheroid, you start to see the morphology of the galaxies much more clearly. And the upshot is that with MAVIS we'll be able to take the deepest optical images that we've ever taken, just because we have that big mirror feeding the system. And then finally, a case here which is looking at Lyman alpha substructure. So Lyman alpha has kind of been a very, there's a lot of newspapers about Lyman alpha. Right? It's been a real explosion of that because of the incredible sensitivity that MUSE has, not just because it's a very efficient spectrograph on a big telescope, but because the background treatment that you can do to see weak emission with a spectrograph is so much better than you can do even with well-tuned narrowband imaging. And this is always a key science driver for MUSE. And so it can kind of survey patches of the sky and sees Lyman alpha everywhere. So then the question is, well, what are the nature of those Lyman alpha sources? The leakage of UV photons from those systems could be a key part of things like reionization, right, at redshifts of 10. But it's poorly understood, actually, what the Lyman alpha line structure is, which tells you about that fraction of escape and what the cloud structures are, what the objects actually look like, which fold into all the expectations of what UV systems or what UV photons are coming out. So this is a very nice study. It's a busy slide. I apologize for that, but it's a case where we did kind of a survey with MUSE on a lensed system. So we're using Nature's telescope. We're seeing high redshift sources at redshift 6 or 7, and you get some interesting arcs that very they get magnified, so you can pick them out. With MAVIS, we'll be able to image these things and sort of resolve them to understand, are these individual star clusters? So these could be the first star clusters, the first globular clusters in formation. That's one expectation. That needs the lensing. I think those intrinsic magnitudes are sort of in the 31, 32 kind of magnitude regime, but with the lensing, it comes up more into the 29, 30, and then we can get up to MAVIS. And then on lower redshift systems, there's another interesting arc system where that's where I think the sky coverage is going to be key, because there are many of these kind of interesting structures in relatively low redshift systems with high-ish surface brightness to do spectroscopy, but you don't have the guide stars. So with MAVIS, we're running studies to see how many of these kinds of systems we can actually get with MAVIS. But on this kind of object, you can start to do quite detailed spectroscopy on the Lyman alpha emission line structure itself. And you see at low resolution, it just looks like the classic kind of double hump asymmetric Lyman alpha profile. But when you observe it with higher resolution, and this is actually real data, the high resolution is with X-shooter, you'll see a little central peak here, which you wouldn't have seen before. And that central peak is UV escape from that system. So that shows that there is a channel for the UV radiation to escape the system fully. And it's that kind of system at higher redshift that could be responsible for reionization. Okay, just last few slides, sensitivities. We talked a little bit about that. So that's our kind of broadband imaging sensitivity and our spectral sensitivities. This is as of PDR, so these are a little bit out of date, but I think it's still an indication. We always use MUSE as our benchmark. This is the flagship, most sensitive spectrograph on the VLT. So we get compared to it. So we try to keep track of how MUSE is doing compared to what we're doing. We sit a bit below MUSE because we're at double the spectral resolution. So it's just harder for us to get the same kind of raw sensitivity, 10 sigma nanometer kind of sensitivity. But you have to remember this is at double or more the spectral resolution. So we're in that regime. This is a challenge. As you saw in the initial diagrams, there's a lot of optics before you even get to the spectrograph with MAVIS. You have the 2DMs, you have pickoffs for the LGS. We've really tried to optimize this system to have the minimum number of surfaces, but at the end of the day, there is an adaptive optic system in the way. And so it's quite hard to compete with an instrument that has much less of that going on. But we try to hold ourselves to that benchmark. And then just to give you an idea of the sky coverage benefit, this is another comparison to MUSE. This is doing like a deep field study. So I think we went to UDS, ultra deep field south, and say, okay, we have all these targets. Now we want to do a MAVIS study of them all, or a MUSE study of these objects. How many of them can we actually do? And so it's a little complicated, this diagram, but you're pushing down in your guide star magnitude limits. So of course you get more objects as you go to fainter guide star limits. And your curve of growth in the gray here is what you would be able to do with MUSE, pushing down the catalog further and further and further, and staying within the patrol field of the MUSE narrow field mode. And this is after the recent IR LOS upgrade. So this is the maximum field of view for MUSE to access. And then here we have the equivalent with MAVIS, holding in all the the guide star requirements that we have, the brightnesses and so on. The brightness of the guide stars isn't a differentiator here. It's really about the technical field and the fact that with a multi-conjugate system, you can have guide stars that are much further away from your science region and still correct for that region, because you have that level of control over the waveform. that MUSE with a single conjugate system can't do. So basically the takeaway here is that you get a factor of 10 more targets in this kind of star poor ultra deep field. You'll get a factor of 10 more targets with MAVIS than you can with MUSE. So you can build up statistical samples, target the interesting objects and so on with much less constraint. Yep.
Do you plan to have a super seeing mode?
A super seeing mode, like a
Yeah.
a narrow field mode of MAVIS. We will not have that. Yeah, that's been discussed. That could be an upgrade. I mean, the lasers are steerable, and then it's just a question of what you do with the RTC. There's been other clever things like super resolution modes where you kind of between the different wavefront sensors, you're sampling the DM in a subgrid way. So there are various clever things that I think can be done with minimal maybe no hardware changes, just all at the RTC side. But at the moment we have enough, I think, just to deliver the basic mode. And then, you know, this should be a push button system at the end. And so the temptation, and I keep telling, we don't want it to be an experiment. We want it to be a stable facility instrument. But, you know, maybe a future plan.
So what do you expect will be the limiting magnitude of the wavefront sensor?
So we're using these new Saphira detectors, which are super sensitive, super low noise. And so we're expecting something in the JH band is the light that comes to those. And then we're expecting something like 19 and a half. We actually don't have the GuideStar catalogs for them. So that's the main issue at the moment, is that we have to guess at what the infrared magnitudes of the star is going to be. In addition to, you know, is it a double or not? Because there'll be a pre-correction to the NGS wavefronts just coming from the lasers alone. So we close loop on the lasers. There's a pre-correction to the technical field. And then, so we'll already be, you know, sub 0.1 arcsecond PSF coming into the wavefront sensors. And I think a lot of the catalog stars will become multiples and this kind of thing. So that's an ELT problem as well, because they're all doing similar things.
Is there a fixed filter in front of the NGS wavefront sensor, or is it selectable?
There is a fixed filter. There's a broadband dichroic between the science channel and the NGS. And then I think the NGS, because we need to limit the thermal. It's not cryogenic, so we need to cut off the thermal, which is kicking in red root of HVAC.
Yeah, you mentioned JH, and I wasn't sure if it is literally a JHS that you're sending to the wavefront sensor.
I think it may be broad, effectively JH because of the atmosphere. Yeah, but I think there is a 1.7 cutoff or something to stop the thermal background. Yeah. Okay, I think I'm almost done. I thought I would put in a slide. I wasn't really sure what to say here because I'm not taught across all the details of this project, but it's happening here. And I know there's some modes or some aspects are under discussion, but I think it's terribly exciting. And hopefully, you know, from this little overview of what's happening at optical wavelengths and how far the ESO community is pushing their system, and even getting into this what I think is relatively high risk to do this in optical, considering it's not really been done before at this scale. To spend quite a bit of money trying to pull it off. I think it shows there's a lot of ambition there. So it's great that Gemini is getting on board with upgrade ideas for its own AO system. At AO, we're very excited to be part of that. I'm still trying to find a way to wheedle myself into the project, so I get to come back here more often. But yeah, we're very excited to be working on it, and I know the team is really enjoying working with Gemini on this project as well as the rest of the consortium. I know that Gyrmos is still, that's one of the things that's still being decided, is how to pronounce Gyrmos. Is it Gyrmos? Gyrmos Gemini. That's what I said. I know this is going to be one of the key drivers for, you know, the science. So these things have to kind of come scheduled together. But, you know, at every instance, you know, get the teams interacting, talking with each other, and the scientists as well. I think that's the best way. We have the benefit within MAVIS that it's all in one project. You know, so it all comes together, we all integrate it together, and the tolerances are so tight that I think there's no other way to do it. Here it's maybe, you know, a little more forgiving in terms of the performances and so on that are needed, but still, you know, there's a real benefit having the AO and the science feel strongly connected. Would be my one kind of shared experience there. But yeah, this was just to say that it's great to be working with Gemini on this project. And then just a summary, MAVIS is going to be a facility instrument that puts some demands beyond just performance. It means it has to be versatile, covering a broad range of science. Sensitivity is a no-brainer. Stability, getting this thing to work, at the press of a button is very much the easy way. And they have, I think, achieved a lot of that with the AOF at the current status. We're introducing another level of complexity with multiple DMs, and calibrating the instrument is a challenge, because you have a lot going on. And it needs to be robust. The project's tracking well. So phase A was passed 2020. We passed phase B in 2023. We're now frantically putting together documents, which is what I should be doing, not on holiday, but we're supposed to deliver documents like June, July for the final design review, which is currently scheduled for October this year. And then it's we start building things and making stuff. So it all becomes quite real after that junction. Some of it's already become real. We had some long lead items that didn't quite fit. We couldn't wait until October this year to get started on it. One of those being the image slicer for the integral field unit. So that is now underway. We just passed the preliminary design with McDermid last month. And so that's a big work package. They're basically doing the scale changing optics to go between the two spaxel size modes, and the field splitter, and then the slicer unit. So that would be a single unit that then drops in. AO is then dealing with all the dispersing elements downstream of that. And our CCD procurement for the science cameras. So we're going to use the same detectors in the imager and both the IFU channels. I don't know what those are yet because the procurement is all under wraps, but that wrapped up the call for tender closed recently. So that's underway. But yeah, mostly the team is trying to finalize all the documentation. And with these, it's a lot for the October review later this year. Challenges are just the whole instrument is a challenge. Wavefront errors is basically zero as far as I can tell. Sensitivity has to be better than everything else. Throughput calibration overheads is a real challenge. These tiny pixels, tiny spaxels, they don't get a whole lot of light from your arc lamp. So creating enough brightness in the calibration sources to calibrate the thing within your usual couple of hours in the daytime. Plus, you can't run the science in parallel with the AO system, so that has to be all calibrated in series, not parallel. So there's some things here that turn out to be even less heavy than I thought would be. Australian funding for MAVIS is tied to national funding cycle, which has a 4-year horizon, and the instrument's going to take more than 10 years to build, so you can see the problem there. But we have a lot of community support for this in Australia, and I think that will see us through that. But it always makes everyone nervous. And then, the team logistics of working across the globe for such a complex instrument, I think is a real challenge. But the team has a good spirit, and who needs evenings? And with that, I will stop there. Thanks.
Are there any questions for Richard, either in-house or online?
I'll go. Time resolution for your imaging mode. How fast can I read it?
Good question. So we will probably have a fast read mode, which will be, I don't know, of order 10 seconds. That will have a higher read noise. We do have requirements on the brightest things we can look at. And we have some neutral density filters for if you want to do bright sources that just need short exposures. Yeah, so we'll have a fast read mode. And if the science is there, we'll make that sort of a supported mode. I think it's there for testing and non-common path calibration, things like that, but it should be there.
I've had targets for decades that I've been wanting to look at, but we found it with a deep imaging with Hubble, so we couldn't go and do 20 series.
Right.
I'm kind of jealous.
Yeah.
That's really great.
Yeah.
And then
Interesting.
as Gemini North size operation, who is doing the software for operation and data reduction?
So the data reduction software is being done by AO. So as I said, I was involved with Muse back in the day. And we really had to push them to make the data reduction part of the overall project, because it was the usual thing that you come with this super new instrument and there'd be no software. You'd have some IDL scripts from the instrument scientists, but there's no supported pipeline. So ESO sort of shifted that, I think, with their second generation instruments, and now they make that part of the project. Yeah, so that's going to be a deliverable, and we're taking inspiration from the existing news pipeline primarily, because there's a lot of similarity in the data format. You know, it's an image slicer for the spectrograph. The imager is pretty straightforward. We have some innovative parts around PSF reconstruction, which would be relevant maybe for the GNAO project. And so there's a couple of different pathways to doing a PSF reconstruction from the AO telemetry itself. So from what the wavefront sensors see, can you reconstruct your wavefront? So that's great. You don't need a source in your field, for example. And it wouldn't help with this instrument anyway, because the PSF over here is different than PSF over here, and your science object is here. So what do you do? So we have a two-pronged approach. So one is a parametric approach called tip-top, which may, considering LAM as part of the GNAO project, would probably be incorporated into GNAO. This is a parametric, I don't know how many parameters, like 5 to 10 parameters that you will tune over time. So you'll do some calibrations over the first year or two of operations, and you'll tune, your measurement of seeing and, I don't know, temperature. I don't know what the parameters are, but you basically build up some knowledge to have a pretty good parametric view of the PSF. We're going to deliver that with the data as an extension in the data products per exposure. And there'll be a grid of them for the imager, because the PSF is different across the field of view. But we're also storing all the telemetry data, which will be the biggest data output of this instrument, is going to be from the real-time control. Because people are like, well, people have algorithms to make use of this, and maybe in the future they'll want to do something clever. So we have like a terabytes of data just on the wavefront sensor information, snapshots, that we'll keep as kind of a science product. That's the current plan. So that's not really a data reduction thing, but it's a data flow thing. The data reduction is going to follow the standard recipes that have been established for other instruments, but we'll have this a version of the PSF or an estimate of the PSF attached to every exposure. So that's something that AO is doing. From the operational side, we will be keying into the operational environment of ESO. And again, we are doing some innovation there for the phase 2 preparation using this tip-top PSF estimator, because you might have different guide star configurations. You want to understand, what does a PSF look like with my science target? Should I get these stars or should I get those stars? The classic problem. So we want the user to be able to forward plan that. It has a direct impact on the sensitivity, because if your point source is like this or like this, your exposure times look pretty different. So they're having to think a bit about their phase 2 preparation, OBS prep tool, how integrated the PSF estimation, how all of those things. That's sort of a work in progress. But they need to figure these things out for ELT as well, because it's exactly this kind of, everything is AO in ELT. So they need to have good answers for that. Yeah.
So the data products that the users will be able to download will be like coarsely reduced, like have a reduced version of the data as well as the raw data. Like I can choose not to download the telemetry or all the way.
Correct. Yes, that's an optional download. Yeah, so the telemetry data will be like a science archive product of some kind. We haven't figured out exactly how to make it available, but it will have a connection to the science exposures somehow, probably just timestamp. Then the data flow has some different requirements. So they have some kind of quality control levels at ESO for, like, on the mountain, do I repeat the observation block or not? And so there's some automated things there. Then there's sort of daytime QC work, maybe in Germany, that has like higher level, how good is the wavelength calibration, that kind of thing. And then there's like science archive products. And, so some users will just use those sort of phase 3 or something products directly for their science. But we also have to make the pipeline available for custom reduction. So you kind of have to cover all the bases.
And the GEMS was really painful, or is painful to operate at nighttime. So you're gonna, and this is like super complicated.
Yes.
So That's gonna be a challenge.
It is. I know. Yeah, it is a challenge. The one thing that gives me hope is that they are running this AOF facility very efficiently. So they have, sometimes not all the lasers are working, this kind of thing that happens. But in terms of slew acquisition, open the shutter, I think they have this relatively down, but that's with one DM. And so I think that the real complexity, and we're gravity stable, so it should be a much better environment than Jim's had being on Cassegrain. This is on Naismith. So I think that alone will help. But you're right, it's 3 wibbly wobbly mirrors, and they all have to do just the right thing at just the right time. And that sounds tricky to me. So yeah. But Francois is on board, right? So he made
Yeah.
surely he's learned from that experience.
He was half sick trying to make it stable though, right? I mean, it was a hard work, so. Yeah.
No, it's going to be a challenge. I think the DM technology has improved as well. Like the DMs are better behaved. Our environment will be much more stable. EASL will not accept an instrument that needs an army every night to make it work. They'll just say it's not ready yet.
Yeah.
So we're going to have to demonstrate all of those things for sure. Yeah. Okay.
All right, let's thank Richard again. And I think, yeah, if anyone has their lunch, I think Richard's
Richard,
gonna
did you
be
bring
I'll come
your
on lunch,
out
yeah.
on the lanai in a few minutes.